Right, so continuing on with the notes here, we left off with continuity. And to show that a function is continuous, there's three things that you have to do. You have to show that the limit from the left side is the same as the limit from the right side. So that's the two pieces, limit from the left, limit from the right. And then the third piece would be that the function actually equals that limit value at that particular c. So what that looks like is, in this example here, they want to know, is the function continuous at -3? So the first thing I'm going to look at is, what's the limit as x approaches -3 from the left side of this function? And if I plug that into, from the left side would fall into this domain, so I'm using that first piece. Let's see, square root of 25 minus x squared. If I plug -3 into this, it gets square root of 16, which is 4. So the left-hand limit is 4. If I look at the limit coming in from the right side of -3, that would be using the second piece for that function there, which is x plus 7. So I would have -3 plus 7, which gives me 4. So the left-hand limit and the right-hand limit agree. And then the third thing that I need to do is I need to evaluate the function at -3. Make sure that there's actually a point defined at that value there. So if I look back at the function for g of x, it says plug into that function. -3 would fall into this first interval here. So if I plug that -3 into the first piece of the function there, I also get that outcome of 4. So we showed that the limit from the left, limit from the right, and the function evaluated at -3 is going to give us that same outcome of 4. Now here's the part that's the tricky part. We got to explain our answer, and you need to write this in complete sentences without abbreviating certain things. So we need to say something like, since the limit from the left of -3 and right of -3 has an outcome of 4, and g of -3 equals 4, then g is continuous at x equals -3. It seems long, it seems wordy, but that's the explain, or sometimes they'll say justify your answer, and that's what they're looking for. Be very careful that you don't abbreviate things like right, don't make it RT, things that, maybe you're used to abbreviating. Things that you can abbreviate, G is what they called the function, so we can use just G for that, it's fine. But just be real careful of abbreviations because they tend to mark things wrong that way. All right, let's look at the next example. It's the same idea. Function's a little bit more complicated, but it's the same process. And we'll have that same kind of little statement going on there too. Let's bring this back down here. Here we go. All right, so we need to look at the left and the right limit. So the limit as x approaches 0, coming from the left side, for f of x, and for the left side of 0, I'm looking at this top piece here. So that would be a 1 minus 2 sine x. So if I plug in 0, I'm going to have 1 minus 2 sine of 0. The sine of 0 is 0, so I have 1 for that left-hand limit. If I look at the right-hand limit, that would be using this second piece here. I would have e to the -4x. And if I do direct substitution, I'll have e to the -4 times 0, which is e to the first, which is e to the 0, which is 1. So the left limit and the right-hand limit are the same. The third piece then that I need to show is that the function, and they called it f this time, that f of 0 is also going to give me 0. So if I plug 0 in, 0 is defined in this domain right here, less than or equal to 0. So if I evaluate the function, 1 minus 2 sine of 0 gives me that 1 again. So I showed that the left-hand limit, the right-hand limit both give me the same outcome, and the function evaluated at that c value, which was 0, also gives me 1. The function's continuous. So here's my justifier, my explain. Since, and you can use the same statement all the time, since the limit from the left of 0 and from the right, from the right of 0 as an outcome of 1, and f of 0 equals 1. F is continuous at x equals 1. So it's a bit wordy, but that's what you need to do to get points for that justification there. All right, the next piece just kind of summarizes everything that we've just done here. So we're going to combine together these two concepts of continuities and derivatives. So this statement here is kind of interesting. All functions that are differentiable are continuous functions. So if a function has a derivative, it has to be continuous. But the converse isn't true. All continuous functions are not necessarily differentiable. And we'll look at a situation, or a couple situations, where you have a function that's continuous, but it doesn't have a derivative everywhere. It's not differentiable everywhere. So if you look at this first example, it's a continuous function. It's a differentiable function. It's a nice smooth curve. There's no sharp points. If you kind of draw some tangent lines along here, you know, you have tangents that are, slopes are negative, slope is 0, slope is positive. So everything is fine there. You can find a slope at any of those particular points. Some situations where you have a function that's maybe not continuous or not differentiable, or maybe some of each. The second one, your greatest integer function. This one actually, your calculator won't put it up here, but you actually have open circles on the ends here. Because that's the value where it jumps up to that next integer. So if you look at that function, the function is not continuous. Well, if it's not continuous, it can't be differentiable. If you think about in terms of slope, if I'm looking at, I don't know, let's pick this point right here when x is 1. When x is 1, the slope for this line here has a slope of 0. That's from the, from the right-hand side of 1. From the left-hand side of 1, the slope, the line is down there on the x-axis, has a slope of 0, but the height is at 0. So coming from the left side, the limit would be 0. Coming from the right side, the limit would be 1. It has two different limits, so it can't have a derivative. It's not continuous. So that's your greatest integer function. For number 3, if you look at this absolute value graph, coming from the left side of 2, you have a slope that is negative 1. Coming in from the right side of 2, you have a slope that is positive 1. But right at 2, it doesn't have a slope of negative 1 or positive 1. It flips immediately from a slope of negative 1 to positive 1. So there is no derivative, or I can't find the slope of the tangent line at x equals 2. Because it's not a nice smooth curve there. It flips from one slope to the next slope. So it's not differentiable at 2. It is differentiable anywhere else, though. If you look at this point back here at negative 1, we said the slope is negative 1. At negative 3, it has a slope of negative 3. Over here at, I don't know what this is, maybe 4 or 5, it has a slope of positive 1. Here at 3, it has a slope of positive 1. So everywhere else it has a derivative, or it's differentiable, but just not at that one particular point. And there's one other situation where we won't have a derivative. For something like this, usually fractional exponents this happens on. So my derivative over here is positive values, but what happens at 0, my tangent line ends up being a vertical line, and the slope for a vertical line even though this function is continuous, at that point at x is 0, we don't have a derivative because the slope is undefined. So if you have a function that is differentiable, meaning it has a derivative, then it's got to be continuous. So that's what this guy here is saying. So differentiability means it has to be continuous, but not necessarily the other direction. You can think of the absolute value graph, the ones with the vertical tangent, that sort of thing. They're continuous functions, but they don't have derivatives at particular points. So when you're looking at a graph, 3 things to make something a function not differentiable. If you have the sharp point, if you have any vertical tangent lines, and then if you have any discontinuity, any jumps or holes in the graph there, you won't have a derivative. All right, just a couple examples here. If you look at number 7, if you look at that graph, absolute value of x minus 3, and you can graph it with your calculator. It's looking like that. And it says at these particular values, at negative 3, is it differentiable? Well, let's continue this graph up here. At negative 3, the slope is going to be negative 1. So it's differentiable at negative 3. There's no sharp points or holes there. At 0, the slope is negative 1. So it has a derivative, has a slope at that point. At 3, now I'm at the sharp point. So it's not differentiable at x equals 3, but it is differentiable, or it has a derivative, at x equals negative 3 and also at x equals 0. So that one's okay. If you look at example, let's skip down to example 9. If you look at the graph for that one, this one, I'm thinking it looks like this. You can graph it with your calculator and see. I think it's this one. It kind of comes down here, does that, and does that. So if you look at this graph, it says, is it differentiable at negative 2 and positive 2? Well, no. At negative 2 and positive 2, we have those sharp points. But it is differentiable everywhere else. If I look along here, maybe at negative 3, you got some kind of negative slope going on. At 0, it has a 0 slope. Over here at 1, it has some kind of negative slope. So it's differentiable everywhere else. So not having a derivative is just talking about specific points, specific places where that might happen.